Good. Very good. Glad to be here.
Excellent. So next, we have Dr. Dwayne Tannant. He's a professor at the University of British Columbia in Canada, and also he was the first place winner of the Global Mapper Master last year. We're so happy to have you here. I know you had to wake up really early to join us today, so thank you. I hope you had your coffee. You're ready to go. So, Dr. Tennant,
Almost ready to go. I was going to find a way of sharing my screen.
oh, okay. I'm going to give you the screen. So Dr. Tennant is going to be sharing with us how to map tree density using Lidar data, which is a tool for wildlife risk assessment. Dr. Tennant, I'm going to give you the screen right now, and you should receive a message, and then you can take it over. See your desktop. Thank you.
Yep. Give me a second. Okay.
Actually, I only see you now, not the screen anymore.
Oh, it's paused.
No worries.
Bear with me.
Sure, of course. No worries.
Can you see the screen now?
No. So if you look on the right-hand side on your menu, you're going to see on the top a menu that says sharing. And then there is an arrow that says show, and there's a drop down that's you can select the screen, and you can select which screen that you're going to share.
How about now?
No.
Oh boy. Maybe I'll just share my whole monitor.
Yes, he has it.
Can you see the presentation now?
Nope.
Okay, we'll solve this soon enough.
You know what, Dr. Tennant, if you would like, I have your presentation. I can certainly bring it up on the screen for you. And if you don't mind, just tell me when to do the next slide, and I'll be happy to do the next slide for you. How about that?
Sure, we can do it that way.
Does that work? All right.
I'm flexible.
All right. Thank you for being flexible. I'm going to take this over. And all right. So I believe your presentation is out on the screen now. Can you see it?
Yes, I can.
All right, great. So I'm gonna go. You can just say next, and I'll be your. All right. Hold on.
So I'll start by saying in the presentations today, we've had already 2 presentations go by Vincent, a nice presentation dealing with wildfire, looking at the end results of fire, looking at the burn severity. My presentation is perhaps dovetailed with that in the sense that this presentation looks at the use of Global Mapper to make an assessment of a wildfire risk in an urban environment in this case. And this environment happens to be where I live. So you're looking at an orthophoto loaded into Global Mapper. And so there's a community of homes on top of a mountain in the center of this image. And there's a ring of forest around this mountain. And I live in a city called Kelowna in British Columbia. It's an area that has very dry dry summers. and is definitely exposed to wildfires. And so the forest around that community that's on top of this mountain is dominated by ponderosa pine and Douglas fir. These are tree species that have adapted to living in areas that are relatively dry, particularly in summertime. And prior to the arrival of people in this environment, typically the forest would experience a wildfire roughly every 20 years. And through that process, the forest would be, thinned out or destroyed and regenerated. Of course, with people being present, we've been suppressing wildfires for the last over 100 years, and we've generated high fuel loads in our forests. So next, please. And so what you're going to see is essentially the same site viewed many different ways. And here I've loaded in a polygon showing property lines in this area. And in this area, on top of the mountain, only on top of the mountain, there's 140 single-family homes and some 25 multifamily buildings. At the very, very top of the mountain, there's a large water storage facility and an important communication tower. And around this cluster of homes on top of the building, on top of the mountain, is a almost 50-hectare lot, a single lot that's a city lot. And there's only one road in, one road out to the homes on top of this mountain. So that's a little bit relevant for wildfire risk assessment. Next. So I was able to access Lidar data for this area. It's publicly available, and as it turned out, the corners of 4 tiles kind of fell into the area of interest, and so I had to use 4 tiles of Lidar data. So that was 164 million points, and the density, average density of that Lidar data was around 16 to 18 points per square meter. Once I loaded it in, I trimmed it down to get a little bit smaller, down to 62 million points, just to be able to more easily manage the data. Okay, next. Next slide. So the previous slide was showing the actual Lidar. It's easy to see the houses and the forest there. And while I did have access to a digital terrain model for the area, I simply decided to make my own. So I constructed a digital terrain model by classifying the Lidar data, basically looking at the ground and removing everything other than ground, and then creating this image of the digital terrain model. So you can see that, the elevation scale, red being the highest and green, blue being the lowest. You can see that I've also loaded in building outlines. I could have used the classification tool to identify buildings and their outlines. I did not do that. I did have access to a building outline shapefile, so I simply loaded that in. So what you have is here is the elevation with the building outlines laid on top of that, just to give you a sense for how the terrain is situated. Next, please. Of course, once you have a terrain model, you can start to look at slope. And so this image simply is a representation of the slope angle. And you can see around the top of that mountain, which is somewhat flattened off, it drops off quite steeply. So there are lots of places where the slopes exceed 35 degrees, 45 degrees, and maybe even slightly higher in spots. And that's a bit relevant for the wildfire aspect, because in a forest that's under fire, the flames and the fire will travel quickly up a slope. And so we have a situation here where we have over 150 homes, almost 200 homes on top of a mountain, surrounded by a steep slope that's forested. Okay, next. One can simply make a contour map using the digital model that was generated. And so this is a contour map of that same area. And I threw the water tower under color red. That's the highest structure present in the area. And the rest of the homes are in gray. And then you've got a contour map. And the contour map, again, shows areas where there are very steep slopes, particularly on the north side. There's a couple steep areas on the west side of that mountain. So it's easy to generate all these different views of the terrain, starting with the Lidar data. Next, please. So part of what I needed to do was to identify trees. So I did some classification earlier on to get that digital elevation model, but I was mostly focused on classifying the trees. And I don't do this type of thing very often. And so it was relatively easy for me to play with the tool that was available. I was using version 24, so I didn't have the more advanced features that Jeff was showing on the previous presentation. But it was fairly easy for me to play around with the parameters for the tree identification. And I did do a bit of a trial and error to make sure that I was doing a decent job of classifying the trees. And so the green points here are the trees, the orange buildings and brown ground and the gray unclassified. But I was particularly interested in the trees. And, you know, one could argue that my classification isn't working ideally because the buildings and trees are kind of blending a little bit, but I wasn't worried about the trees adjacent to the buildings. My focus was, where are the trees in that large ring of city property that surrounds the homes? And go next, please. And you know, there was some mistakes right near the buildings, but I wasn't too concerned about that. They weren't important to me. And next, as Jeff was commenting, the ability to run really quickly profiles through the Lidar point cloud, in this case, the classified point cloud, is very useful because you can quickly determine whether or not your classification is making sense, whether it's working. So this is two profiles, one down the north side of the mountain and one on the south facing slope. And you gain immediately confidence that the classification of the trees are working because you can kind of see the trees and your ground classification is working. And so I did that. As I was playing with the classification parameters for the vegetation. And once I got to a point where I was pulling off virtually everything that was trees with high degree of confidence, then I was happy with that tree classification. So certainly running profiles through your classified point cloud is really valuable. Next. So there they are. I've classified the trees. But then I went one step further. There's a tool that uses the classified trees to identify individual trees, because the previous one is just, there's a bunch of green points that are vegetation. They're vegetation points, not trees. Here now I've identified trees. And so there's almost 50,000 trees that were captured in the area of interest. And I only wanted to look at trees that were higher than 3 meters or 10 feet in height. Next, please. Once you've identified the trees, it's you can go and kind of bin them to different tree heights. So the colors there are showing the tree heights. The scale's a little bit mixed up there, but the red ones are the tallest trees and the green ones are the shortest trees. And you can see how the tall trees are clustered together in certain areas on the mountain. By using the property boundary for that city lot, I was able to instantaneously kind of select just the trees in that lot, and that's what I've done. So we went from 50,000 trees down to just under 10,000 trees. So in that one city lot, there are roughly 10,000 trees. They're colored by height, and you can pull off some attributes for each of those trees after they've been identified. And for example, the mean height of all those trees, just about 12 meters, the maximum height around 33 meters or 100 feet. And if you have the number of trees and the area in that yellow city property line, you find out that the average tree density is around 200 trees per hectare. Next, please. Well, 200 trees per hectare is a little bit too dense for that type of forest in that type of environment and climate. So professional foresters have recommended that the maximum tree density be only around 100 trees per hectare. Once you exceed around 100 trees per hectare, if a wildfire were to occur, it would burn at a higher intensity. And of course, with homes being located nearby, you don't want a wildfire burning at a high intensity. High intensity would really infer that the fire climbs up into the tree canopy and jumps from tree to tree. And so we're sitting at, on average, twice the recommended density for the trees for that type of forest and that type of environment. And there is a density tool. So the trees were all identified, and it's easy to also plot the density. So in this case, the tree density per hectare, that's what the color bar scale is showing. And areas that are red, and in fact, areas that are probably yellow, the trees are too dense. And this is an area where the trees should be thinned to manage the wildfire risk for that area. So that figure right here is probably the end result that's most important for perhaps guiding wildfire fuel management. And it's relatively easy to go from LIDAR to vegetation to trees, and then to tree density as a workflow, and then to generate it obviously in these map views. And so you can start to assess what areas need to be thinned or not. Next slide, please. I also used all the building outlines and created a buffer zone around all the buildings. And so these, this red line, and if you look really carefully, there's a kind of a purple line running around the buildings on the top of the mountain, is just simply using that buffer tool in Global Mapper. There's a desire when you're dealing with urban forest interfaces to look at a couple different zones. A distance of 30 meters away from a house is an important area where you want to make sure that the vegetation is appropriate and not too thick. And then a zone running out to about 100 meters away from each individual building. And by using the buffer zone, I can look at where are the most important areas. And so areas outside the 100-meter buffer zone are lower priority for fuel management. As it turns out, on this particular example, there's 3 little sort of red polygons on the mountain that fall outside of the 100-meter buffer. But generally speaking, most of that city property is within that 100-meter buffer from the nearest adjacent building. To create these buffers, I had to merge buffers from multiple buildings because there's hundreds of buildings captured in this image, but that was a relatively easy task to perform. Next. I just wanted to sort of back up and describe why I did this work. It was sort of a personal passion project because I live on that mountain. And this is a photograph I took last August from my deck of my house on that mountain. And I'm looking at a wildfire that is a fairly substantial distance away from my house at the time. And when this photograph was taken, homes were already being burned down. You can't see them; they're behind a ridge. And that fire started on an afternoon. In fact, my wife reported the smoke from the fire to our BC Wildfire Service. She was one of hundreds of people phoning in to report that fire, and it lingered. The fire lingered for a couple of days and was very small. Then the wind picked up. We had a period of high wind, and that fire grew very, very rapidly, traveled across these ridges and started to burn homes. And this is what kind of was motivating me, because the smoke became much thicker than what you see here as the day went on and as it got dark. And in fact, my university that I work at, fire jumped a lake, traveled, sparks, burning embers were blown distances of up to 4 kilometers. So jumping ahead, starting other fires. The fire approached my university. The university was shut down, evacuated, and working from home is when I started to do this little passion project to take a look at my little community. Next, please. And so the lower arrow is pointing to my house, and the upper red arrow is pointing to a ridge that burned this past August. So this is a photograph taken in November. The fire has been, the fire season is over, and the fire is gone. But in this image, you're looking at between where I took the photograph and my house, the lower arrow, that forest that you're looking at right there, based on the mapping I did, that's about 300 to 350 trees per hectare. And so the thinning would need to take almost 2/3 of those trees away to get down to the desired tree density. And that ridge above, this is what it looked like after the fire. Yep, go ahead, next slide. So I walked over to I drove over and took a walk through the area that did burn this past summer. And this is kind of the end results. The tree density here was probably sitting around 300, maybe 250 trees per hectare. And the burn severity would be probably moderate to high. Now, one could use the technique that Vincent had shown us using the raster calculations, using satellite image before and after the fire to actually map out the burn severity. But on the ground, based on my understanding of burn severities for wildfires in our province, this is what moderate to high burn severity would look like. Of course, if you had a home in this environment, there's a chance that that home would be lost. And so that's really what's motivating my use of taking the LiDAR, creating these tree density maps, and then providing that map free of charge to the city to hopefully aid their decision making and budgeting for fuel management to help protect our community and my house, because it was a fearful time when you see this big wall of flames travel tens of kilometers in essentially 6 or 7 hours. So that's my presentation. Thank you. And this is what, that last slide, if you want to go back to that last slide. So this is what 400 trees per hectare looks like. This is probably 150 meters away from my house. So this is the stuff that keeps me awake at night in the summer during our wildfire season. And wildfires are something that we have to live with, and managing our fuels is very important, and therefore providing tools to identify areas where fuel management gives you the biggest bang for your buck is probably important. I will say that it's estimated to cost about $10,000 per hectare to do that fuel management, and that was that city lot was 50 hectares. So 50 hectares times 10,000. It's a substantial amount of money, and that's why you need all the ammunition you can possibly obtain to convince the city to spend money to protect my community.
Absolutely.
Thank you.
Yeah, absolutely. Well, thank you, Dr. Tannant, for that incredibly informative and insightful presentation on mapping tree density using LiDAR. I'm certain that your work has been a great resource for anyone performing wildfire risk assessment. So we have some questions coming in, the first of which being, is the city open to funding the thinning of the trees?
So since I prepared my presentation, and there's a short report that goes along with it that I gave to the city, the city has made an argument that they are managing the fuels, because occasionally a tree will die adjacent to a road accessing that community, and they will remove the tree. They are doing prescribed burns. They will remove trees, either chip them if there's easy to access with equipment, chip them and haul away the chips, or they will cut them and burn them, usually this time of year in the winter season. As it turns out, on my particular mountain, before those houses were built, some 25 to 30 years ago, they thinned out the trees. Since they've been built, they have done nothing, and the tree density is, trees grow, and trees die, and they fall over, and that fuel begins to accumulate. So I and my neighbors have seen this presentation now too, and we're all motivated to put some pressure on the city to spend some money. So $500,000 will solve the problem completely. But even if they were to spend $100,000 in targeted areas, I think it could have a substantial impact on the fire risk for our community.
That's amazing. That's crazy. So we have one more question. Did you have to take any above ground utilities into account when performing this?
So in that LiDAR data set, that community is only 25, 30 years old. Everything's underground. There's not a wire to be seen above the ground. There's a street. So from that perspective, the classification is not finding wires because there isn't any wires to find.
Excellent. Well, Dr. Dwayne Tannant, thank you so much for joining us today.
Okay, thank you. Enjoy the rest of your day.
Thank you, you as well.